simple. Should I say it now? I mean, I don't know if I should. The You guys know what the intermediate value theorem actually is? You guys want to read it to me? Anybody have their book? Intermediate value theorem. This is under the topic of continuity. Okay? So I'm going to sketch a picture for you guys. Probably two pictures. It's a really simple kind of thing to go about. Here's your x-axis maybe. Here's your y-axis, right? So let me go back and use the exact language of the book. Just so some people can alleviate their anxiety if they have any, like, you know, they go, oh my God, you, Mr. Judge, you evil man, you didn't talk about intermediate value theorem, and now I'm, you know, going to have a heart attack with that. So let's find it, okay? Let's get it out of the way. It's not that hard. All right, so where's our, I think it's 2.5, right? Section 2.5. All right. Okay. So essentially, here's kind of what you have to have. First of all, you got to have a nice, beautiful what? Continuous function. Okay? And then they give you something like this. This is over an interval AB. All right? So they pretty much say this. Let F be what? Continuous over what's called a closed interval, AB. Okay, so kind of like saying, okay, here at this point and this point, you have a nice, beautiful what? Curve. Is that right? And that's because it's over this particular closed interval there. So you go, okay, over that interval, we have a nice and what? Continuous curve. Now, there's more. So F is continuous. N is any number between. So I'm going to write it this way. And F of A is any number between. Here we go. These are the output values. All right, so here's the deal. F of B. So this N is between F of A and F of B with these outputs not equal to each other. Okay, so let me express you guys what they mean by that, right? So this really here is the location of F of A. And I didn't draw a nice enough curve, but okay. I'll say this is where F of B would be. So I'm going to kind of make it maybe I guess I have to do it a little bit more dramatic. Okay, so try to be more dramatic. I'll do it like that. Okay. Okay, and what they're saying is N, that N is right in between. So like this. Let's do it that way. Okay, so here's an N value here. It's really on this axis over here. Okay, so I want you guys to see this extremely important detail. So you have a continuous function over a closed interval where f of a is less than or equal to n, less than or equal to f of b. This is the n. Notice it's between what? These two things. All right, so I guess that's really the focus here. Okay? And sometimes they like to say let, but sometimes they'll say if. So suppose, yeah, if. Then, this is your conclusion. Then there exists a C in the open interval AB such that f of C is n. Now, here's really what they mean, okay? So I'll let you guys read that, okay? Here's the conclusion here. Okay, so there's going to exist a what? A number C such that f of C equals what? That value n. That's called the intermediate value. Intermediate value. Okay? Intermediate merely means between. So you might say, well, what is that? It means this. That there is some value they call, and what color? I guess it's green. There's some number that they'll call what? C. Where, you know, f of C is that value n, because these are the coordinates. This is C comma what? N. Right, there's the n. Now that's it. That's all. This is the very famous intermediate value theorem. I like to abbreviate it IMV, intermediate value theorem. And it's based on the, you got to have a continuous function. So it's an application of a continuous function. So we like that. So what I'm going to say to you guys now is this, ladies and gentlemen, okay? You might say, how is it very much used? Well, it's used this way. Okay, this is kind of how they use this intermediate value theorem. They're going to do the following here. Okay? This is like the value A, and this is B. So this is my location, f of A, and then this is the location of maybe what, f of B. Here's your function f. Now this is what they're doing here. Okay? I want you guys to note some observations here. This is extremely important. F of A is less than 0. What do I mean by that? That this number is what? Negative. You guys okay with that? All right. Bless you.
Thank you.
F of B is what? Positive. This is a positive number. And you might say, how do we know they're positive and negative? Well, they're on the y-axis, right? Now, here's kind of the key. Here's the key idea. What does this actually mean? You know what that means, ladies and gentlemen? I'm going to call this, we can call it C, but I'm going to call it R. Why did I call it R? What is that? F of R equals, what's this address? Isn't that R comma what? 0? So F of R equals what? 0. Why did I use the letter R? Do you guys know? What's so special about the letter R? R is known as a root. Okay? So if I give you guys a definition, and I'll say, what's the definition of a root for the function f? Well, a root r, that's f of r equals 0. That's a value r, a number r such that f of r equals 0. This is what we call a root of a function. That's by definition. So we care about those roots. We care about the zeros of a function. We really like those locations, okay? It helps us a lot. So what's nice about the intermediate value theorem is if I have endpoints, okay, like, when I'm out of colors. If I have endpoints where one point is positive, one point's negative, those y-axis, f of a and f of b, then, and f is continuous, then I can guarantee there's at least one root in the function because of that nice and continuous function. But this is a very specific case of the what? Of the intermediate value theorem. It's a very specific case. Intermediate value theorem in general doesn't require f of a or f of b to be positive or negative. It just requires that they're not the same. That's why we say not equal. And, you know, all they're saying is that there's going to be a value in the interval AB such that, you know, f of c equals that n, or in this case, if you have this kind of situation, even if you have the reverse, right? You might say, what if I have the reverse here? Well, as long as they're what? Opposite and your function's continuous, if one's positive and one's negative, you will have a root r. That's all. There's going to be a root. So it's a very, very popular question to finding roots. So we use the intermediate value theorem to determine really roots of functions. And then that's really what I wanted to kind of mention, you know, in that example. So, you know, the book has a lot. I think the book has a few examples. And it's really simple. So let me see the book there, 2.5. Finding roots. Like, for example, maybe they said, okay, f of x, the cube root of x plus x minus 1. They're going to say show f has a root in the interval 0 to 1. Very, very, very popular kind of question here, okay? And what they want you to know, first of all, is this. What do you guys know about this function? This function is a nice continuous function. It's continuous over the interval 0, 1. So we know it's continuous, right, over that interval. So what do you guys notice? If you said, I'm going to plug in a 0 here, right? Don't you get the cube root of 0 plus 0 minus 1? What does this equal? Does that equal negative 1? Okay. You guys okay with that? If I plug in 0, don't I get a negative? Here's my point. You get a what? A negative value here. What happens when you plug in 1 here? This is now the cube root of what? 1 plus 1 minus 1. The cube root of 1 is what number? What do you guys notice about that number? That number is what? It's positive. So what I'm saying is focus on those two results. Negative and what? Positive. So you have the situation we're describing in this picture. Your function is continuous. What do you guys know? I'm going to say you're done. Say, why do we know we're done? Because we're supposed to show f has a what? A root in that interval. You say, how do you know that we showed that? Well, here's what you say. You cite by the intermediate value theorem there exists an R such that f of R equals what? 0. That's what they want to say. Okay? There exists a root R such that f of R equals 0. And you say, why? Because isn't 0 between -1 and 1? That's it. That's it. Now, let's look at Desmos. Right? You might say, can you do this in Desmos? Yeah. Let's go Desmos. Let's say this. I'll put y equals cube root. This is x raised to the 1/3 power. Okay. Was that plus x? I don't remember. Plus x minus 1. Okay. All right. And you guys know by now, I don't like the red. I like, And the thing about Desmos is this. You see that interval between 0 and 1? You guys with me on that? Didn't we just show here f of 0 is -1, and we showed f of 1 right up in here. Oh, it doesn't show me. Okay. If I get close, it's kind of f of 1. Well, we don't care what it is. It's 1, but it's positive. So I have the negative value, the positive value. This is what they mean right in here in the middle, that you have a root in the interval between 0 and 1. And that's nice because the function's continuous, So it's just a simple application of continuity. And, that's kind of what I wanted to share with some of that. And then, what else to say? Sometimes I'll say that the book actually hid this question. The book hid this question this way for you guys. Here's the book's version. They say, show there is a value of x where the cube root of x equals 1 minus x. So this is the book's version. I took this from the book. In other words, x is not a root here, but x is simply called a solution to the equation, right? So x here, so that it has a solution, there's a value of x. And it has to be in the interval 0, 1. So show there is a value of x where, and that's just code for saying you have a what? A solution to the equation. Because ladies and gentlemen, if you were to try to solve this, there's really no way you can solve this equation. There's no algebraic way you can solve the cube root of x equals 1 minus x, so you guys know. Okay, so you say, well, can I solve it by factoring? No. Can I solve it by any other algebra? Actually, no. There is no algebra where you can actually solve that equation. Believe it or not. So what's starting to happen, if you guys want to know, I'm going to put this, there's no algebra. Usually we say, hey, use algebra, right? But now we're going to say there's no what? There is no algebra. So there's no algebra you guys can use here. But which is, it's starting to open the door. I mean, I know it, and I know why I give it to you, and I know why I want you to think about it, because later on we use it in the theoretical result. But what this is also opening the door to is a way to find a root. In other words, there's other methods that exist that use calculus to find roots, believe it or not. This is where, what's this course again? Calculus. And we'll see this in our future. Although our future isn't today. Okay, but in our future, we're going to use calculus to find roots. So calculus is nice and can find roots for you. In fact, it's so nice that even in Desmos, when I touch it right there, where do I touch it? If I touch Desmos right here, the location of the root, do you guys want to know what Desmos did? It used calculus. It didn't graph it. Although you say, but Mr. Judge, I see a graph. I know you see a graph. There is an algorithm you use to graph. That's fine. But to find that numerical answer that I'm holding on, the root of 0.3177, which is the same thing you guys see here, okay, calculus was used. Exactly. Calculus 1 was used to get that root. You go, really? Yeah. You gotta stay tuned. That's coming. It's not today though. It's coming. That's one of the joys of calculus. Is it's a tool that can be used now to find something as simple like just as a root. You say, well, that's a different kind of. Why did you graph? Well, what I did here is I solved. Right? This equation here is the cube root of what? X plus x minus 1. Okay, in other words, you can say, did you translate or did you move those terms? Yes. And then we called this function here, by the way. This is the name of the function we just found. That's f. So you might say, what does this have to do with the intermediate value theorem and in our future? Well, these are kind of the same questions. This is the f. In other words, I labeled this function cube root of x plus x minus 1. Sorry. Yeah, I was fine. That's my f, and we're trying to find where f of x equals 0. Now it's a root question. Okay, so I just want to kind of share with you what the book was doing here with these, with this particular question. It says, hey, can you give me a solution? Well, that's equivalent to saying, can you give me a root for that function f? Yes, you can, and you could use the what? Well, let me take this back. We can show there is a root, but we don't know what it is. That's the intermediate value theorem to show that you do have a root there. Finding that root, ladies and gentlemen, finding that root, you got to stay tuned because it has everything to do with what? Calculus. All right, you guys okay with that? All right, now let me give you guys another hint since I wanted to use this stuff today. This is really the intermediate. I'm going to change this title. Okay, it's not derivative formulas. This is going to be intermediate value theorem and the secant line. So, intermediate value theorem and what? Secant. So we're going to give you guys some theoretical information here today on this. A nice theoretical information day. All right, so there you guys go. Finding some value r, that's the definition of a root of a function. And an important way to do that. So you might say, well, okay, you got the intermediate value theorem that tells me that there is a root in an interval. But how do you begin to find it? Okay, stay tuned. But what we'll see in our future, though, if I go to my website here, okay, I'm going to go to, I don't want to go out of Desmos. There we go. Let's go to, you guys aren't in statistics, box plots. Right? We're going to go to Math 261 here. So let's start to talk a little bit about what this is, just to give you guys some theoretical results. And then hopefully our internet is good. Okay, worksheets and videos. Secant and tangent lines. Okay. So I'm going to bring this into to notability. All right, so now that we're in notability, let's look at some of these notes. And let me share with you guys some geometry now. And it's related to calculus. This is what we're doing. I'll give you guys a lot of notation. This is in your notes, or at least you could go to the website, right? And you can look that up, okay? But what you guys see is a nice curve, and then you see 2 points, right? So what are the 2 points? You got, very often we say, here's point P, right here, and then here's point what? Q. Now, when you have 2 points going through any curve, ladies and gentlemen, draw a line. And you say, okay, what is that line? It's in red here. Drawing that line through the 2 points. This is called, or this is the definition of what we call a secant line. Any line that goes through 2 points in a curve is a secant line. Yes, it's defined in terms of the coordinates, though, of the x and y coordinates. Okay? Now, go back to beginning algebra. Say beginning algebra? Yes. What do I mean by beginning algebra, right? In beginning algebra, first of all, let's think. You have the equation y equals what? mx plus b. Do you guys remember that? From beginning algebra, the graph, that's the line in red, by the way. So all we're looking at is this beginning algebra. You see this number here, though. What's so important about m? What's m in beginning algebra? Yeah, so ladies and gentlemen, m is the slope of your line. Good, good. M, yes, that's called the slope, and that's the change in y value divided by the change in x value, which is also y2 minus y1 over x2 minus x1. So this goes back to beginning algebra, where m, you guys are right, is the slope of that line. Good. There's your m. And then you say, well, where did I get these coordinates? Well, that's x1. And this is really, you know, if you guys wanted to see it that way, this is these are the coordinates. All right, this is your x1 and your y1. x1, y1, and this is x2, y2. Okay? That's beginning algebra. Does that look familiar? Okay, good. You got the slope of the secant line, because this is a secant line. Okay. Now what do we have here? Oh, I'm going to change the letters. You go, you're changing the letters on me, Mr. Judge. Yeah, that's x1, y1. And remember, this is beginning algebra notation. Now, what do you guys notice about the letters? I changed them to what? Does that even look familiar? Say yes. What do you guys see here? You see A and F of A? Ah, it's starting to ring a bell. That's the same A and F of A you guys may have already seen in your life. And then this is an arbitrary X and Y, really. Okay? So what do I mean by arbitrary? Well, any X, any Y. This is really the Y value, right? It's the same line, same definitions, by the way. Now, here's what I'm going to do. I'm going to change it even further. You go, what do you mean? Well, A, F, A, and then what's this? You go, how did you get A plus H and F, A plus H? Well, here's what we did. Okay, notice what H is. H, ladies and gentlemen, is found this way. This is where A is, and then over here, this is A plus H, okay? It's these X coordinate values. You guys okay with that? So the distance between them, this is an extremely important detail. The distance between, we call what? That's the H value. Okay, you guys okay with that? That's H. So there's your A coordinate. There's your A plus H coordinate. Okay, we're on our way. This is like looking at the X coordinate and the Y. This is the X and Y for the other point. So you might start to say, is my slope defined? How do we define that slope? Do you guys know how, if I said this is y2 minus y1, x2 minus x1, it is, but notice this. This is going to start to look familiar. Okay? This is going to be what? F of A plus H minus F of A. These are, if I want to share with you guys, for example, these are the y coordinates. Maybe I'll just use that for the y coordinates, the green. Okay, you guys see that's the green. And then what do you guys see over here? This is the x coordinates. So here's what I want to show with you guys. This is now A plus H minus A. So you now have the x and y coordinates. Now, you might start to get to the idea that, you know what, I'm starting to see something here. This is, by the way, called a difference quotient. Difference quotient from algebra. Actually, pre-calculus, ladies and gentlemen. Pre-calculus, we call that a difference quotient. So you have f of a plus h minus f of a, everything over, what's the algebra here say? This is over what? And that's m secant, right? Is this starting to look a little familiar? You go, boy, Mr. Judge, the slope of that secant line is a difference quotient. It's the very famous difference quotient from really pre-calculus. And that is starting to look like the definition of a what? Derivative. It's not the definition, though, but it's looking very close. Okay, so far so good? These are the notes, ladies and gentlemen, I put on my website for students. You know, I was going to use this as for lecturing. Just on a nicer H. So this is kind of like the algebra geometry of a derivative, if you guys want to really know the truth. And it's related to the very question I just shared with you guys earlier, really, about finding the root. It's really related. Oh, my God, this is the picture that eventually we'll use again, you know. And then you go, Mr. Judge, what just happened in this next slide? In this next slide, ladies and gentlemen, you might say, what is that? What is that called now? This is now what? This is called a tangent line. All right? A tangent line. Where's our other point? There's only the point what? P. You guys okay with that? Now, what's going on with that tangent line? That tangent line, we say this is, and this is the author of the book. Don't get mad at me. This is Stewart. That tangent line is thought of as kissing the curve. So this tangent line is kissing the curve F at the location A, F of A. So you're not going through 2 points anymore. It's really going through only 1 point right over here. but you're now kissing the curve. That's what the author describes as a tangent to a curve. It's actually kissing that curve. It's not going through 2 points anymore. Now you say, how did that happen? Well, you know what they did? Here's what they did. They said, okay, if I went back to this and I said to you guys, let's let the point Q approach P. Q is approaching P. So this is the Q point, and it's getting closer along the curve. It's getting closer and closer to what? To P. You guys okay with that? So maybe we should put it in red. Q is getting closer and closer to what? To the point P. Now, how is it really doing it? You're really doing it by saying that X value, A plus H, over here is getting closer and closer to what? To A. And that's what I just wrote down. Because you're getting the X coordinate there, remember? So when you say Q approaches P, they're really saying A plus H is approaching A. And if that's happening, what does that mean about your H value? H has to be going at 0. Why? Because it's gone. That's the same H. So that distance is shrinking. H, the distance between A plus H and A, called H, is going to what? 0. And so when that happens, ladies and gentlemen, you now get this definition here. Okay? You get the definition that M tangent is that limit, because this is a limit, as H goes to 0 of that difference quotient we just described. A plus H minus F of A, everything over what? H. That, ladies and gentlemen, is where you get, geometrically or algebraically speaking, your M tangent in this picture. Now you say, what in the world is M tangent? Well, it's a couple of things. What's M tangent? What do you guys think about this here? M tangent is the slope. Go back. Let me find the color. What is M tangent? It's the slope of the line tangent to the curve. Right? Isn't this, don't you have an equation? Y equals M tangent X plus B. It's a slope of the line tangent to the curve at this location. A of A. Slope of the line tangent to the curve at this what? Location. Notice what I'm saying. It's the slope of the line tangent to the curve at this location. It is also known as, what is this also known as, ladies and gentlemen? It's that F prime of A. Yes. It is the definition of what? Derivative at A. So when you guys are doing your homework and on your test, and you're trying to find that F prime of A, you really just found the slope of the tangent line at that location A. That's a derivative of the function at A. That's what you've been doing all along. This geometric what? Picture. I'm going to say it again because this is a moment in your life for why you've been using that. Haven't we been using that definition? Yes. You've been finding the slope of the line tangent to the curve at that location, geometrically, algebraically speaking. This is that blue line out tangent. And that's what you've been using. Now, you might say, Mr. Judge, what in the world? Remember I talked about the intermediate value theorem? And we said, okay, how is it? Okay, we can use the intermediate value theorem in theory to know that there exists a root in an interval. Is that right? All right. Well, this particular function, the way you're looking at it now, I could draw another picture. If you go back to intermediate value theorem, where was that one here? Okay. See this picture? This is going to happen in our future. Oh, I think it's in Desmos. Is it still in Desmos? Yeah. Let's go to Desmos here. Okay. Desmos. There you go. I can kind of do something here. And again, this is all theoretical for you guys. But I want to illustrate a quick point because we're really not there, but it is related to the topic that we're talking about, which is what I want to do. I want to share with you guys that idea, okay? So I'm going to import this add to the intermediate value theorem and see if I can make some sense so that I can refer to this one day in your future and say, hey, do you guys remember we talked a little about this and where the geometry, remember, I can bring it up. In your future, this curve, if I can move it, I might be able to move it. There we go. Is that line kissing the curve? It is. Okay. Good job. So here is that value A, just in the picture we just drew. And what we're going to see in our future here, there's the root of that equation. But in our future, essentially, we're going to be finding that equation, L tangent, right? This is this equation that has y equals mx plus b. We're going to locate that intersection for the line. And that location is going to approximate your what? Root. So we can now start to take all these curves where you can't really find a root algebraically speaking, but you can numerically approximate the location by actually using L tangent, that equation of the line tangent to the curve. That is going to approximate the curve. You can say, really? Yes, because remember, this is curve, this is f, right? So I know I'm giving you a lot of high-powered information. So that L tangent will approximate the curve f, is what I'm saying in short. And then if it approximates it, remember, this function was like a cube root. Remember that? Remember the original function we put down? You said, okay, that's a cube root of what? X. I think it was plus x minus 1. Is that right? Well, I can approximate that particular function with what? With a linear equation from beginning algebra. And if I can do that for points around A, then I can approximate the root. And that's essentially how Desmos finds that location I showed you guys. And I'm actually kind of lying to you in a little bit. You say, what do you mean? Well, let me express to you some of the differences between Calculus 1 and Calculus 2. In Calculus 1, we can approximate a function with a linear equation, the derivative function there. Remember that? We get the slope, that whole thing. In Calculus 2, we get to do some of this stuff again. But this time, we get to approximate functions with higher order polynomials. That's deep and powerful. And you know, I lecture in that course too. I have videos with that too. But, you know, I'm just kind of trying to motivate you with the theoretical result of why you care about finding derivatives. This is only one reason. There's many reasons. One reason is directly related to that intermediate value theorem question. The intermediate value theorem can only be used to show there exists a root, but it doesn't find the root. Then you tell me, but Mr. Judge, how do I find the root? Continue with calculus and you'll find a root. You'll approximate it. That's coming. That's under applications of derivatives. It's a way we can apply what we're going to talk about. You guys are nice and motivated now. A lot of times when you go with that theory, people go, "Oh my God, forget about it," you know. But I mean, if you're looking at it that way, you got to remember and ask yourself, why are you here? You know, because I got some 241 students. Sometimes they get mad about learning things. So why are we here again? To what? To learn. We're not here to play. Those days are gone. Was high school fun? No. It wasn't fun for me. I hated high school. I was glad to be out of high school. I was free after I was out of high school. But for some people, high school was fun because they got to do what all day? Play. They played. Like, yeah, you're right. And then they come to college and they go, "When's the playtime, Mr. Judge?" And like, sorry, there's no more playtime. It's over. Now we get to do some what? Calculus. We get to learn why we care about that derivative, why we care about that definition we've been working so hard. So I did want to share with you guys that. I don't know.